Danville. South Danville. Okay. All right. Well, I think we can get this going. I think we just got a couple of people don't mind signing in. Pick this off. Yeah. We'll keep it a try here.
Yeah.
All right, is this thing on? Yeah, all right, sounds like it. All right, so I want to welcome Dr. Erica Weiniger from Sonoma Technology. He's got over 30 years of experience in providing data-oriented solutions to air quality problems and challenges. Currently, again, he's working at Sonoma Technology as the Director of Industrial Services, and he's had previous engagements at Air Toxics Limited, Exponent Inc., Radion, and then spending a majority of his career as an independent consultant. And Dr. Weiniger is going to present on the practical signal detection theory. So have at it.
Thank you. Oh, great. We lost one already. Damn, that's not a good sign.
Just wanted to sign the sheet. Robbie, you didn't sign the sheet. You should not be here.
Oh man, I haven't even started talking yet. I'm already losing the audience. That's not a good sign. Jeez. Anyway, so I was talking to our sole participant, but as a secondary participant, of course, I welcome you to ask questions as well. So we'll make this pretty informal since we're all kind of in the same boat here. The concept I want to talk about is that in fence line monitoring, particularly open path type of situations around refineries or chemical plants, same kind of idea, is it's a detection question. And ultimately that go back into theory is signal detection theory. What is a real detection? What's the signal that you detect, and what's a false positive or end up being, could be a false negative? And so there's a lot of theory about that. And so I'm going to go buzz through that fairly quickly, but talk about the practicalities of doing that. Because essentially everything comes down to, is it there or not? And do we have confidence in what you say is there or is not there? And that has ramifications in many ways, particularly in the fence line refinery world. That's, pretty tightly monitored by the agencies and the public. So, but the first thing I want to do is kind of introduce you to what I call the patron saint of human-based judgment, Stanislav Petrov. You may not have heard of this guy, but he's a Soviet, can't remember his position, but in the Soviet military in 1983, his job was to watch the screens that would detect incoming missiles from the US to hit Russia or Soviet Union in those days. And one night, the screen started to light up. Oh no, incoming missiles, a bunch of them. And so if he had followed the algorithm, and this is the ultimate big umbrella concept, do you follow the algorithm, or do you have human judgment in the picture to validate what the algorithm says? And we all hear a lot about algorithms these days, social media and all that stuff. So we're kind of beset by the fallout from algorithm processes. So the big question is, which one, where does the human fit in that picture? So the algorithm was saying, press the button, well, inform the generals, inform the leadership to retaliate because the bombs are coming in, the nukes are coming in. But he looked at that and he used his own judgment and he overrid the algorithm. And it turns out there was sunlight reflecting off of clouds that were being shown as incoming missiles. So potentially he could have, if he had followed the rules, he could have unleashed World War III and the end of our normal civilization. So I look at that as an example of how to use human judgment and not to rely on the fallibility of an algorithm, because in my mind, the ultimate weakness of the algorithm is that it does not have ultimate knowledge of all pieces of the situation. if we had, 10 supercomputers that knew every little bit of information about the system you're monitoring, maybe, but that never is not going to happen, particularly in a monitoring system, environmental monitoring system. The problem here is too much data, too little time, and too little of the deep knowledge that I just mentioned about the entire system. So this is an example of in the real world, what we're talking about. Over here, this is what we're currently doing at Sonoma Tech. We have 8 refineries or other industrial sites, 100 open path systems, a bunch of other sensors, including some Picaros, don't know how many exactly, but essentially we have a lot of data come in, 1.2 million data points per day. How do you manage all that data without going crazy? So all these inputs and the outputs are to 8 public websites. All the refineries are in California, and they're required under the regulations there to have public websites. So output was into those websites on a 5-minute basis. Periodic, like quarterly reports, we do go in and validate. And a big thing is to minimize false positives, because a false positive gets everybody upset unnecessarily, right? False negatives is another bad thing, of course, because but the ramifications aren't as immediate. But the impact of a false positive is that ultimately it reduces the trust in the agencies and in the community for the data that you produce. Oh, it's another red herring again. It's another, false alarm. So again, back to the signal detection theory, there's a whole bunch of math that you can get into, but ultimately you have a signal amidst a bunch of noise that you want to detect with confidence. But you have to also understand what happens if you do have a false positive or false negatives. And ultimately the question is the signal detected? So as I started at the beginning, I said, ultimately the practical question is it there? Is it a real detection or not? And, this is kind of the graphic of the kind of decision. You have a decision tree to go through at different points, each to the question. Minimize false positives and false negatives. You've probably all seen this and forgotten what a null hypothesis is, as I have to remind myself about every time I look at it, even from 30 seconds ago. But basically, type 1 error is a false negative. Type 2 error is a false positive. So here's what we want to avoid. In fact, I did an error, and it should be the other way around. But public-oriented, the false positives and false alarms invoke high response. This is, if you can reduce this whole question down to a single graph, this is our objective. So here on the x-axis is the false positive rate. We want to have as few false positives as possible, right? And on the y-axis is how many you actually do get. Now, a classifier is basically the tools, the decision process you use to classify as a detection or non-detection, or it's a false negative. There's 3 choices. And if you can track that and plot over time, this is where it goes. So the one-to-one thing is a random classifier. Basically, if you just took by chance, one thing or the other, that's your 50-50 thing ultimately, right? And as you move the curve up, you're getting closer to a perfect classifier. And again, this is just another diagram of that decision tree that I'm talking about. So in the technical theory terminology, that's the classification methodology. Now, we all want to know about the practical aspects of this. So ultimately, it comes down to having a complete quality assurance program. And I saw a term just a few days ago that really crystallized for me what that means, to have some automated processes combined with the human-based process. And that term is augmented intelligence. You've probably heard about the, people are afraid about the big AI is going to take over the world and turn on us humans and all that stuff. I don't know, different opinions on that, but at this point, people that I've read, they basically say the artificial intelligence that we have now is basically great for augmenting human intelligence. So the combination is really good right now because the AI that is currently in place, most of it is machine learning, which is basically trial and error and trying to get correlations. There's no real intelligence going on there. So you have rules. You basically have rules that the machine follows on an input and classifies them one way or the other. And I'll talk about some of those rules in a minute. So how do you implement the quality, effective quality assurance program, or in our terms here today is a decision theory process? Well, when I look at the entire ensemble of what has to go into implementing this kind of a system, you have design. How are you asking the question? Is your monitors, and we'll go into that, where you put them, the citing, data collection methodologies. So you have that step down, and then it's operations. You maintain your instrumentation correctly. Now, and I'll show some examples. Are you keeping your mirrors clean in your open path systems? Do you change filters on instruments? All those kind of practical things in operations. And then at the end, of course, you got all that data coming in. What do you do with the data? How do you process that overload of data? And here is the QA system ensures the process. I put a little star there because if you look in the quality assurance literature, there's quality management systems and there's quality assurance systems. Ultimately, the grander term, the bigger term is quality management. And then under that, you have quality assurance, which is various procedures, and quality control, which is looking at individual data streams. It can get confusing until you've really gone through it a lot. So what are the issues in terms of setting up this kind of a program? What's the prime objective? And of course, I always like to reduce this down to how are you asking the question? Because any kind of a measurement, whether it's a single measurement or a whole fence line or community or a country, you're asking a question. Is the air quality good? Is it bad? Is the light on? Is the light off? You can have a whole range of things, but it comes down to a question. And so what are you trying to detect here? And there are multiple answers to that question. And that, of course, defines how you go. I used to, when I worked at the lab, people send odd questions to me all the time. And the first question I'd ask them is, what are you going to do with the data? Just say, I need to do some air sampling. Okay, that's fine. What are you going to do with that data once you get it? And that then directs you to how you're going to measure that, do that air measurement. So this is just an example of some various types of objectives. Generally, for these kind of programs, we're talking about adhering to some kind of a regulatory rule. So there's a lot of instances where emergency response also is in place. One of the first open path systems I was involved in years ago was at a refinery where some years earlier there had been a release and it had impacted an elementary school that's fairly close. So they put a fence line system in there, and that was the target so that they could have an emergency response in case there's an incident and they can notify the community. There were no rules and no laws in place, no regulations to have a fence line system, but that was kind of the first line of defense. So I've talked about how are we asking the question, and there's factors that go into that, kind of emissions, your target species, the topography of the site, what's the meteorological conditions, where are the communities? That's a big point as well, of course. And then what other programs are going on? A lot of times things overlap. Some of the refineries we're doing right now, they have the RTR, the passive benzene sorbent program testing in place concurrently, but that has a weeks-long delay, and so they're doing those monitoring in parallel. And then different plants have different types of things. There's not one type of refinery in the world, so some of them have an HF process. There was a big thing in LA, big HF alkylation blow up several years ago, and that forced a certain type of monitoring. And so we have a Picaro HF analyzer in the community because of that, actually. That program is ending soon, though, by the way. So in any kind of monitoring program, you have various stakeholders. I separate stakeholders from the public, even though the public is a stakeholder. Because you have agencies, you have community groups, public, and of course, the facility is obviously a major stakeholder. In the current rules, and for the, as far as I can tell, any type of Fenceline monitoring is going to, a lot, if not all of it, is driven by public demand. So ultimately, the public wants to see the data. So that includes non-detects, which is, I always say non-detects do have value. Everybody. And kind of a little bit of a caveat is that in terms of citing where the monitors go, oftentimes people say, I want this in my backyard. Everybody wants to know what the air quality is at their house. There have been many instances where I'm doing monitoring for some other purpose and people complain, the closest agency monitoring thing is 10 miles away. What about my neighborhood? You know? And so that's hard to manage you know, in terms of setting up a program because, you know, the loudest voice, the squeaky wheel theory works, but you have to resist it as much as you can in order to not twist the objectives too much. Other types of issues in terms of developing the program, what kind of instruments? Again, we're back to the how do you ask the question. So this is just kind of a rundown of a bunch of different monitors. So we have point monitors, which I mentioned a lot about OpenPath because that's kind of sexy because it uses lasers and stuff. Anytime you use lasers, people are excited, it seems. But you know, it covers a wide swath of space, and that's a real advantage, of course, because you don't have to have a bunch of point monitors. But there are parameters that you can't have in OpenPath, and that will be the answer to that is point monitors. So particulate of PM 2.5, PM10, ultrafine particles, black carbon, which is basically soot, as from combustion sources. All of these factors here are need to be point monitors. And there's various gases that aren't amenable to OpenPath, and so you need to go to GCs. Can I have a ring a bell to you guys? Chemiluminescence detector for, and that's actually a special case. Chemiluminescence detectors for hydrogen sulfide. Though I know Carl has an H2S monitor, we do use some of yours as well, but that's one of the common approaches to doing hydrogen sulfide is with a chemiluminescence detector. And then OpenPath monitors, as I mentioned, for a larger path. Various types there. UV dose and FTIR are the most commonly used. Tunable diode lasers are for more specialty applications, and quantum cascade lasers. They're really not used much at all for OpenPath, but can be. But with an appropriate setup, you can have a reasonable detection limit. By reasonable detection limit, it has to be close to the REL, the reference exposure level, the health-based levels. Doesn't do anybody any good if you're getting non-detects at some level that's way above what the health levels are. And you know, there's been the last 10 years, there's been a lot of development in the low-cost sensor space. Mostly that's for particulate. PM 2.5 is the dominant thing. Coming up from behind are some VOC sensors, but they're way behind basically in terms of sensitivity and selectivity. So these other more expensive and comprehensive technologies are going to dominate for quite a while, right? So we talked about citing and methods to do that. This relates back to my comments about the community. We're monitoring the fence line, not in the community. Now, a lot of times programs do have a fence line, the fence line set up and a community component, because it's obvious you have a refinery or a chemical plant, let's say a big facility, you know, you have stacks and the stacks go up and over the fence line, at least part, if not most of their emissions there, and that can't be captured by the fence line. So community monitors are useful and I would say imperative to really assess the entire impact, entire impact from the facility to the community. And many of our programs do have that, but you know, in my opinion, I think when you say a fence line, it should be more of a facility monitoring, fence line and downwind. Infrastructure is kind of the hidden need behind the technology, because when you're talking about setting up a light beam that has to traverse 1,000 meters and back, when you have a little bit of misalignment, you can lose a significant amount of your signal or all of it. And so because of that, you require a significant infrastructure. And that's just for the alignment. There's other aspects as well. You know, with any kind of instrument, you have heating and cooling demands. You can't just put a box out in the sun, those kind of things. And this ends up being actually a large chunk of the implementation of a decent fence line program. Some of the types of infrastructure you're talking about, the one on the left, so it's elevated because of the topography in order to get a clear beam path, you know, so, and here you see these pretty good, good sized pillars for stability of the open path instruments. And again, that's the alignment question. And these, of course, have to be sufficiently robust to last for the duration. So no Home Depot sheds. Public notification system is a key part of these. The goal, of course, is public transparency, and community wants to know if there are exceedances, and they want to know when it actually happens. Not, oh, by the way, you breathed in a bunch of bad stuff yesterday afternoon. And so that uses preliminary data, because all that data comes through can't be, unless you chain a 50 people to computers 24/7, uses preliminary data. And so much of that is automated QC logic. But the systems that we implement as part of the overall QA program, if there are exceedances, then there is the 24/7 on-call response where that data is reviewed. So if there is a false positive or a hit and it ends up being a false positive, we may not be able to stop it immediately, but we can do so relatively quickly. So I talked earlier on about the decision rules. Is it a good detect? Is it a not detect? This is kind of the basis for that. These are the automated QC rules in the decision process. So some of it is before the instrumentation is done. So that's deployed. That's the bump test. So you do that on a quarterly basis, and you have your assurance that the instrument is working by itself correctly. Measurement quality. This is looking at the spectra that come through from the instrument, and I'll show some examples in a minute. Various instrumentation type, instrumentation specific aspects, signal intensity, parameters related to that. And this is for the two general main types, UV and FTIR. Just different parameters that are looked at and different objectives in that preliminary data review. So again, going back to my first comments, is that the human knowledge, the deep systematic knowledge of the entire system relates to the decision data quality decisions. So if there's an issue with a detection, some of the things the analyst will look at is like having is the alignment in? How does that relate to, is the signal sufficient, or is there some other indication of some alignment problem, like high winds, for example? So those kind of things. Low visibility, was it a foggy day or a dust storm, or California last few years have been lot of wildfires, right? So that can drift in the area and cause visibility issues. Reflector and optics issues, and then how the concentrations are relative to the reflection of it. This is an interesting thing because what if you get a really high value and then a really low, some blip? Does that make sense that it just come high, a spike, and then go back down? Those are kind of things that can happen. And, everyone wants to know what happened. Well, most of the time you can't explain it, in my experience, but it's important to review that. And that's kind of the process, is to catch those random spikes that can happen for some unknown reason. My experience, you can't, most of the time you can't figure out why, but it just happens. So you got to manage it. So some of the deeper details about some of those things are to achieve a high level of temporal completeness. So here's, one of the retroreflectors. So just keeping those maintained, simple maintenance, like changing the oil in your car. So inspecting the optics, there's all sorts of detailed aspects of the individual instruments. Talk about bump tests for ensuring good operation and accuracy. And our experience is that working closely with the manufacturers of the instruments is important, because they may have some little bit of wisdom to impart. If something strange is going on, they can often help us understand what might go on. Something that's not in the manual sometimes. So again, back to analyzer alignment. Mentioned all of these things. Some close-ups of some optics and retroreflector degradation issues. So you can see, trying to get dust, flaking of the reflective surfaces and the like. And some of the facilities are fairly close to a marine environment, so that, of course, doesn't help the situation. So again, I'm hammering on this decision process thing. Have some real-time data validation for first level processes. So various very detailed aspects, signal intensity, things that don't require a lot of judgment in there. So it's easy to say, what's the signal intensity, drops below a certain threshold. It's not so easy to say why. And there's a number of things like that as well. Integration time, all of that goes into that raw number that can be indicative of something going on. This is the formalized process. So the various parts of this can be automated, various parts can't be automated. So we have a system called Insight. I mentioned that to Robbie. This is where we take all of these 1.2 million data points a day ingested into this system. Part of it is the automated processes. Part of it goes through twice per day process where a human being actually looks at data. Then there are very automated alerts where analysts will separately look at an alert function, an alert process, and decide whether that's some kind of failure mode or whether it's real or not. But ultimately, the objective is to get down to this level 3 review. This is, by the way, this is the formalized EPA process, level 0 through 3. And so we follow that process. So here's some rule-based data processing. So here's some different target, different aspects to be checking for, here's various tests, sticking as if a value stays the same over an extended period of time. What's the chance of something being at, some value for an hour or two without any change? Unlikely. Missing, there can be various reasons for that. Glitches or some failure mode. And then we have operational codes that come from those detailed instrumentation parameters that I mentioned. Here's I have a couple of examples of some UV spectra. The way this is processed, we have different regions that are looked at. So this is the background. That's the signals. This is subtracted from the signal, and we there's a fitting process of to a reference of the actual detected measurement to a reference spectrum, and you get an R squared, a correlation coefficient, and there's a threshold for that. If it's below that threshold, then it's a poor fit and not a good detection. Example of benzene. This isn't as good of a fit. You can see that it's a little noisier around the peaks. So here's an R square of 0.72. You know, you can look at it and think, it's not so bad really by my eye, but from the statistics standpoint and the thresholds that are set, it's below the R square for that is 0.8 threshold. So this would be a non-detect. And here's benzene again. That is a good detect. R squared 0.93. So you can see again here that the noise in the signal is much lower. And so there's a higher level of confidence from the map. So, you know, do we look at that previous one, say, yeah, it's probably there? Well, you could in one case. It depends on the predetermined threshold that you want, level of confidence that you want to have in the detection. You know, do you want to report, yeah, we kind of think it's there, but we're not going to bet the farm on it? Or do you want something that's like, yeah, it's there solidly? And so that's, you know, overall, when we're talking about hundreds, thousands, millions of data points over time, you want to have a set level of confidence. And that's what this is. So back to my cool term that I found, augmented intelligence. You need to collect and process data in real time, do some automated QA/QC, all the other stuff that goes into data things, security and management processes and the like. And the solution is ultimately you have this fancy set of systems, but in the middle of it is a human being. These are the various processes. Key here to looking at these things is the solid line being, that's where the human being is more involved. So you have these automated things, you collect it, store it, do this processing, but then you data review the user-defined query. Let's look at that one set of data. It looks kind of fishy. Visualization, that's one tool to look at things. You know, is the data sticking, or is there a spike that looks out of place, etc. Data quality indicators, what are they telling you about the system? And then looking at, this is the other thing that from a history, what's your familiarity with how things work as a system? That's the correlation of instrument with operation and maintenance. So it's one instrument, everyone's run into this. It's like with cars, you know, that guy's a little clunker, even though he's just a couple years old, but you got one that's next door, same age, works better. How do you know? There's something in there, but you have a knowledge of that. How do you program that into an automated system? Possible, or fairly so. And then ultimately, we talk about just distributing the data to stakeholders. So I beat this to death in terms of automated data quality. These are just some of the QA operational codes that are done automatically and assigned to the data stream. Talk about the automated alerts. So these yellow boxes is where the human beings are involved. Then again, identify the problem, communicate the action. And we actually keep a record of those instances. When there is a human intervention in the data stream, we keep a record of that. So if there's a question retrospective about what happened in that instance, we have a record of what's going on. And I mentioned visualization. This is the kind of thing that is done. Where I've had people come to me, how do we figure out this data? Well, first you got to look at it and plot it and use our born-in human pattern recognition facility to try and understand what's going on. And then the final data validation, either on a piecemeal basis, on a per day basis, but then I mentioned the deeper overall system validation on a quarterly basis, and that's compiled and put into kind of a permanent record. That's what goes to the agency, and you know, ultimately over time they'll look at that performance and see how well the system works. Shoot. talk about human-based error recognition detection. Okay, and this is an example of the external display data coming out on a routine basis. So how do you indicate in a concise manner you've got a lot of data streams coming in, whether you've got hits or non-detects? And so this is one way that this is visualized. These are all the different paths in the system, different parameters, and different codes. Here's our point monitors and indications that it goes into this color-coded thing. So you can glance at that in a second and figure out what's going on. And then you can look in deeper here. Here's kind of a typical community-based thing on the website. The community can look, just call that up, put it on the phone, and say, "Oh, what's our benzene like today? 8.6, pretty high today." And another capability is to look at the time series. So here's the top above the REF, the health level. So that helps everybody understand what's going on. Not only the community, but also the facility. What happened in that time. That's it. Thank you.